Hi everyone. Thank you to the previous two speakers as well. So they made my job a lot easier. They have also pitched the problem. Ruben, thank you so much. I will hopefully present a method to get us to market much more quickly. Probably FE-NAND or like ferroelectric NAND is a way to get us to market quickly. So a lot of you might know me from the last 2 days of lab course. I'm Prasanna from Georgia Tech. I will be talking to you today about an emerging memory solution for NAND scaling. And I will be discussing a few of the reliability concerns and what we could do about them to quickly get us to where we need to go. 3D NAND, so NAND in general is a fascinating subject. NAND started out back in the late 1980s and has since been scaling at the rate of about 50 times in bit areal density over the last 3 decades. It started out as 2D with the feature size around 1 micron and close to the late 2000s and early 2010s, saturated at about saturated at about 15 nanometers in feature size, or close to the early 2010s, and went 3D. Since it has gone 3D, the scaling has been in the Z direction, XY direction, and also logic scaling. So 3D NAND actually started out as a 24-layer MLC product from Samsung back in 2014. Today, a lot of companies, Samsung, SK Hynix, Micron, ship 300 plus layers of QLC NAND with over 5 trillion transistors. And roadmaps project that we will have either 1,000 layers by the end of this decade and probably even 10,000 layers by the end of the next decade. But before we get to any of these, there are a lot of reliability challenges that we need to address. As we bring these word lines close together, we have lateral charge migration that we need to contend with, and we also have increasing variability between the word lines, increasing write voltage. We are already close to 30 volts now. We also have the reducing endurance as we go to the higher logic levels. So over the last 2 years, ferroelectrics have emerged as a drop-in solution to address a lot of these challenges. To your left, we have the first demonstration from SK Hynix back in VLSI 2023, and then we have Samsung's demonstration in IEDM 2023. And to the right here is our group's demonstration in IEDM 2023 as well. So before we do anything with ferroelectrics and ferroelectric NAND, that is a big problem that needs to be addressed, and that is memory window. Anyone who has worked in ferroelectric field effect transistors will tell you that the memory window of a ferroelectric field effect transistor is limited by the coercive voltage and in turn the coercive field. And for hafnium zirconium oxide, which is the stock standard material that we use, has a coercive field of close to 1 to 2 megavolt per centimeter, which at NAND compatible thicknesses of about 20 nanometer limits us to 3 volts in memory window. As I mentioned earlier, today's products are QLC compatible, so we require memory windows upwards of 7.5 volts in order to do multi-level operation. So as we see here, most of the standard FEFET results are on the 2 ECTF line, and at 20 nanometers it's just 3 volts. So over the last 2 years, we have realized that inserting a dielectric aluminum oxide, silicon oxide can improve this memory window significantly. And here are a bunch of different variants of dielectric inserts that we have tried out in-house at Georgia Tech, and we achieved a maximum of close to 11 volts. Here's a quick snapshot of what the industry and academia have done over the last 2 years. Different combinations of materials ranging from channels, ILs, and different dielectrics, and even different composition of ferroelectric materials to engineer the memory window. To make it easier to digest, here's a map of the memory window versus the gate stack thicknesses, and a maximum of 19.4 volts was achieved, was demonstrated back in IRPS 2025 earlier this year. So you might say, what use is a 20 volt memory window if your write voltage is 50 volts? But here is a benchmark showing that memory window and write voltage scale roughly 1:1, and we even have results where amorphous oxide semiconductors were used as a channel material, and Samsung demonstrated close to 17 volt memory window with a 13 volt write voltage. Okay, you might ask where we got this huge improvement in memory window from. The current working theory is that we have trapped charges at the ferroelectric dielectric interface. Unlike the trapped charges at the ferroelectric silicon dioxide interface, which are detrimental as they screen the ferroelectric polarization, the charges that sit far away from the channel IL boost the memory window either by amplifying the ferroelectric polarization or by forming a dipole. So, but that's it. I introduced this method of introducing ferroelectrics in CTF-NAND as a solution to reliability challenges. So let's go over each one of the reliability paradigms, retention, disturb, and write endurance, and see how ferroelectric NAND fares. There are also lateral charge migration and device-to-device variation, but in today's talk, I'll just focus on device-level reliability. So in order to study retention, we started out with 3 different gate stacks. One is the standard 19 nanometer gate stack, plain old heterogeneous FEFET, and then we used a 14-4 silicon dioxide gate blocking layer with a 4 nanometer silicon dioxide gate blocking layer at the top. Then we have our tunnel dielectric layer where we have a 3 nanometer aluminum oxide layer in the middle. So let me walk you through how retention measurements are done. We take the FEFET standard FEFET 14-4 with a silicon dioxide layer at the top. We start out with a 6.5 volt memory window, which is an enhanced memory window. This is done at room temperature, and that is the initial memory window. And we let it stay for about 100 seconds. We see a 14 to 15% degradation in the memory window already in just 100 seconds. And after 10,000 seconds, we see that the memory window has dropped 29 to 30% down to 4.66 volts. Now that I've shown you an example, I'll quickly run through different temperatures. At 75 degrees Celsius and 125 degrees Celsius, we see similar trends. We see 2 things here. One is that the initial memory window at different temperatures continues decreasing, and the second thing is at each temperature, we see 1.5 to 2 volts decrease in memory window. Now what happens when we have a dielectric insert in the middle? Now when we have aluminum oxide dielectric insert in the middle, we see immediately that the 7.5 volt enhanced memory window is constant at all the temperatures. And also at room temperature, we see that the 7.5 volts stays for the 10,000 seconds, which is about 3 hours. We do see increasing degradation in memory window at higher temperatures though. Okay, now I just picked 2 materials, 2 stacks and showed you a plot. Why should you believe me? So here we have a benchmark here. I'm plotting the memory window, initial memory window on the Y and X axis. Everything is sitting beautiful at along the 1:1 line, but this is not how it stays. I want you to focus on the blue dots here. And after 10,000 seconds at room temperature, we see all the gate blocking layer devices where the dielectric was inserted close to the gate at the top have all dropped by 25 to 50%. Why could this be happening? There are 2 reasons. It's a ferroelectric material, it's going to depolarize. The second is we have trapped charges at the ferroelectric dielectric interface. These trapped charges could detrap. So we used Applied Materials Genestra, which is a defect-based modeling platform, and we tried to understand what's going on. So let's start with the gate blocking layer device. We programmed the gate blocking layer device. We have heterogeneous and silicon dioxide here. I mentioned 2 concerns, depolarization and detrapping. So let's go one by one. So when we see here in the overcompensated state where we have QIT prime, which is the trapped charges of the interface greater than the polarization, the field along the ferroelectric layer is non-depolarizing, so no depolarization, which is great. But there is a huge field across the SiO2 layer which causes detrapping of the charges at the ferroelectric dielectric interface. So now as these charges are detrapped, the field across the SiO2 layer decreases, which means there's going to be no more detrapping, but the field across the ferroelectric layer turns depolarizing. And over time, the ferroelectric layer depolarizes, leading to a 2-stage retention loss. So what happens when we move the dielectric to the middle? So here in this example, we have moved the dielectric back to the middle, and we see that the thick heterogeneous layers on either side, the 8 nanometer heterogeneous layers, prevent the detrapping of the charges and hence prevent the second step of depolarization of the ferroelectric layer from taking place. So even after time immemorial, this stays the same. So we have robust retention in our tunnel dielectric layer stacks. Again, a quick summary. We have on the left bottom the standard ferroelectric devices which have lower memory window but decent retention. Then we have the gate blocking layer devices which have large memory window but huge retention loss. And then we have our hero devices, which are the tunnel dielectric layer devices, which have a large memory window at the same time robust retention. So can we not solve this in gate blocking layer devices? No. Cook et al. Showed at IEDM 2024 that you could insert a hafnium oxide layer or a high K layer between the heterodo and the gate blocking layer, and you could probably solve the retention problem. But this also takes me to the next problem that needs to be addressed, which is the memory window temperature instability. In the gate blocking layer devices, as I mentioned earlier, as you increase the temperature, the initial memory window begins to drop. So on the left, we have a benchmark of all the devices, and we have the gate blocking layer devices always having better memory window compared to the tunnel dielectric layer devices, which are shaded in red. So that is the disadvantage of tunnel dielectric layer devices. But at the same time, the tunnel dielectric layer devices has a temperature invariant initial memory window. While the gate blocking layer devices, as you can see here, temperature is plotted as 1 by kT. So when you move to the left, it's increasing temperature. So as you increase the temperature, the memory window of the gate blocking layer devices continues to decrease, which is undesirable. Okay, let me quickly move on to the problem of disturb. Disturb is a challenge in NAND stacks because a pass voltage is applied to unaddressed cells when we are accessing any cell along the bit line. So here I'm showing the IDVG characteristic of our 838 device, where we have a 7.5 volt memory window. In order to turn this device on so that we could access the other devices along the bit line, we apply a pass voltage of VT plus 2, threshold voltage plus 2 to turn on this device. So here we see a benchmark, and when we apply this threshold voltage, this is for the erase and program states, we see that we do not have much of a problem with the erase state, but with the program state, we see 20 to 60% degradation in the threshold voltage when we apply the pass voltages. So how is disturb characterized? So we program the device, we measure the IDVG characteristics periodically, and we apply a positive pass voltage of VT plus 2 n number of times and characterize the IDVG characteristics. Now I am showing a IDVG characteristic of the program state on the left, and I have a tracker for the threshold voltage here on the right. And you will see as more and more pass voltages are being applied, there is a positive shift in the threshold voltage. Here there is a shift of about 2 volts here. So we are applying a positive voltage, we see a positive shift. This is more reminiscent of PBTI. So we suspected electron trapping. So we introduced a disturb mitigation scheme where we apply a negative voltage to detrap these electrons that are trapped during the positive pulses and then refresh the device. So what happened when we did this? We immediately saw results where when we applied a refresh pulse every 1000 access times and every 10 access times, we saw huge improvement in terms of threshold voltage shift. So to quantify it, without any mitigation scheme, we have a 28% degradation in the threshold voltage. With the refresh being applied every 1000 accesses and every 10 accesses, we could reduce it down to 16% and 4% respectively. So in the slides, there are also QR codes for you to access the journal publications corresponding to all the results that are being presented here. So the last problem that I will not go too much into the detail is write endurance. Write endurance, though, is not, we don't require 10 to the 12 or 10 to the 15 write endurance as we require in DRAM. In NAND, we require close to 100K to a billion write cycles. But still, we see that in SLC, MLC, TLC, and QLC NAND, in standard CTF NAND, we see that as we go to higher and higher logic levels, the endurance degrades significantly. Commercial NAND that is being shipped out now, which is QLC NAND, has endurance of the order of higher hundreds to the lower thousands. So if you can see at the bottom there is a benchmark showing all the large memory window FEFETs. And we see that as the memory windows increase, the endurance continues to drop, pretty much similar to how it happens in the case of CTF, which means we should be able to throw this into CTF and make products out of it. But unfortunately, that is not the case. Ferroelectrics have a different problem. That is just endurance. That is the point at which the defect completely degrades. So the problem with FEFETs is that the threshold voltage shifts even when the device is operable, which is undesirable in multi-level scenarios like the NAND. So here I'm plotting the shift in the threshold voltage after 1000 write cycles, and we see that irrespective of what device combination, whether you insert the dielectric or channel material, we see more than 100 millivolt shift, in some cases even close to 10 volt shift in the threshold voltage. This is a work that will be presented at IEDM this year. Please do visit this talk where we introduce a scavenging technique to show flat endurance characteristics up to 100K cycles. This is of course in a small, in a low memory window standard FEFET, but the same principle holds in both cases. Okay, I'd like to conclude my talk by saying that this is a very exciting time for ferroelectrics, and hopefully, if not in FE-NAND, we'll probably find a place in FE-NAND and make it to products over the next 5 years or so. So here is a summary of all the papers that were discussed during this talk. We have a review in MRS Bulletin coming out in this month's edition of MRS Bulletin, which summarizes all the ferroelectric NAND work that have been done up here. Okay, with that, thanks to all our group members and our sponsors. Thank you.